Hello everyone. So we have looked into the different aspects of computer organization. We have looked into assembly coding, we have looked into the processor design part, we have looked into the pipelining. Now we will be moving into a very important aspect of the whole compute system, which is called memory. Now since we have already seen that we are all our architectures are basically stored program architectures or stored program model, where your instruction as well as data is stored in some memory, and then you uh, fetch those and execute them as in the CPU and then store it back. Now in this stored program model, memory becomes a very important aspect, and that is why we will be spending significant amount of time in understanding the different memory technologies. Then we will also understand the motivation behind cache memory, then what are the different classifications of caches and their performance. So that will be broadly what we will be discussing in this segment of the course. Okay. So let me jump on to our discussion. So we are talking about memory systems. All right. So as we discussed that we will be starting with a brief overview about memory technology. Now how actually we store data, that is important to understand to appreciate the different constraints or different design decisions. So we will not go into too much detail, but we will have an overview about memory technology. Now memory can be implemented in different ways. The memory which we have already seen in our discussion so far is basically registers, right. So we have talked about register files and general purpose registers and so on. So now how these registers are implemented? Now before we move on to the registers, let us try to answer this question, like if I want to store a bit, how can I store a bit on the hardware? Now from your understanding and knowledge about digital logic and other basic electronics courses, you know what is an inverter. So an inverter is a gate which basically if I give 0 will give me output as 1. All right. Now can you think of a way to basically store a bit using, let us say, multiple inverters? So one possibility can be that I have two inverters and I connect them like this. Okay, so what I have done? So I have connected two inverters back to back. So the output of this inverter is fed to this, the input of this inverter, and the output of this inverter is fed as an input to this inverter. So the input to this inverter is 1 and the output will be 0, and then 0 will be fed again and it will be 1 again. So if I can build something like this, then let us say if I feed, I have to have some kind of a mechanism to initialize. Let us say I want to feed a 0 here. So I will have some access to this part and I will feed a 0, and then this 0 will remain because this 0 will be converted to 1 and 1 will be converted again to 0, and this will remain in this state as long as these inverters are supply the inverters do get the power supply which is required, right. So this can be a very simple simple cell which can store a single bit, right. Now, of course, you need something else to write and read the data, because you have to write the desired value and as well as read the desired value, and that is where you need some couple of more transistors, which are called access transistors, and this is nothing but a 6T SRAM. So, basically 6 transistors, 6T stands for 6 transistors. SRAM is static random access memory. Now, where from this 6 transistors are coming? Because each inverter will need 2 transistors. So, you need 2 transistors here, 2 transistors here. So, these are 4 transistors and these are the 2 access transistors, which are that is how you get 6 transistors, and 6T SRAM is a very popular memory, which primarily is used in cache, which we will talk about. So, now the advantage of 6T SRAM is that it does not need the requirement of number of transistors is not very high, because for storing 1 bit you are needing 6 transistors, which is reasonably good, and also it's the accessing, reading and writing the SRAM is relatively faster. So, that is why it's very popular. It's dense and it's also fast. So, it is primarily used for caches. So, we will talk about caches, but this is what goes inside a cache. Now, you might have also heard about DRAM. So, DRAM is dynamic RAM. So, there the density is much higher, because for implementing a DRAM you need only a single transistor. All right. So, so if you look at a DRAM implementation, you will see that the implementation looks pretty simple. So, you will have of course, I am not giving you all the details, because that is not the objective. So, there will be a word line which selects like where from you need to read the data, and then there is a single transistor which is connected to a capacitor, and the value is stored in a capacitor. Basically, whatever value you need to store, whether it is 0 or 1, this is stored in this capacitor. Now, because it is stored in capacitor and capacitors are non-ideal, it leaks. So, let us say I charge this capacitor to the VDD value, and if I check back after few, let us say milliseconds, then I will see that the charge has already started going down, because these capacitors, though basically they have resistive path through which the current discharges, and that is why you need constant recharging or refreshing these capacitors to store the value appropriately. That is why DRAM requires frequent refreshing. So, you need elaborate mechanism to refresh or recharge these capacitors in a very short interval, like in milliseconds you have to refresh your DRAM. But the advantage is, since you have only one transistors to build this DRAM, the density you can achieve using the DRAM is very high. All right. So, these are popular kind of memory technologies. Now, we started with resistors. So, resistors actually are you can say that register files are implemented using latches or flip flops. Now, for completeness, I would like to show you how I can very simply build a latch, and from latch I can build a flip flop. Now, what is a latch? As all of you should be knowing, that a latch is let us say look at a D latch. A D latch is a device, or it's a module or device which has an input called D input, then there is a clock input, and then there is a output which is called Q. Sometimes you will have Q bar as well as output. Now, how it works? If it is a positive level edge, positive level triggered edge. So, whenever the clock is high, this D becomes transparent to Q, basically as if this input and output are connected together. If the clock is high, whatever changes in D happens, that will get reflected in Q. And if what happens if clock is low? If clock is low, then whatever was the last value of D before the clock went low, that value will be available at the Q. So, that is where the memory comes in. So, basically it remembers what was the last value of D when the clock was high. So, as soon as clock went low, that value is latched onto, and that value is preserved and supplied to Q till clock becomes high again, and when clock becomes high again, then again D becomes transparent to Q. So, this is what a latch is. I hope this makes sense. So, pictorially if you want to see, like if clock is high, so this is my clock signal, then D, whatever change in D will be happening. So, let us say whatever change happens in this duration when clock is high, that will get reflected in the Q. So, we do not know what was the previous value of D before this clock is. So, we will start from here. So, as soon as the clock became high, it will just follow the value of D, okay. And if as soon as the clock went low, whatever value, let us say the value of D was high, so that value will be preserved till the next clock, till the time when clock becomes high again. So, let us say the clock the D remains low. So, as soon as the clock becomes high, you will see that the Q output will become low, because the D is low. So, it will just follow whatever is the value of D when the clock is high, and whatever was the previous value when the clock was high, that will be latched onto when the clock is low. Okay. So, this is what a latch is. Now, if you think about it, how can we implement it in hardware? We can implement it very easily using a mux. We are already familiar with mux. So, how we can build basically how we can build this D latch using a mux? So, this is my mux. Mux has two input, 0 and 1. There is a select line, and then there is one output, right. Now, my objective is to convert this mux into a D latch. Now, look at what is happening. So, I have this clock signal, and clock signal is deciding what will be my output. And what are the possibilities I have in the output? I can directly get the input as output, or I can get whatever was the last value of input as my output if the clock is low, right. So, I have two choices as my input. One is, let us say D. So, whenever clock is high, then D should be my output. So, I can now say that okay, my select signal is clock. If clock is high, D will be output. Up to this, this should be clear, right. Now, what happens if clock is low? If clock is low, whatever was the previous output, that should be my output. So, I will need to just connect a feedback and say that okay, if clock is low, then whatever was the previous value of output, that should remain as output. So, I will just feed it back as input, and this will be supplied as output for the time till clock is low. All right. So, this looks like a very neat implementation, And if you want to further understand like how this mux can be implemented, so those of you who are interested in going little deeper, so a mux can be implemented very easily using transmission gate. So, I will not go into too much detail, but I will just show you what transmission gate is. Transmission gate is basically two transistors connected connected in a parallel manner. So, one is a PMOS, one is a NMOS, and this is what a transmission gate is. The advantage is that so why you need transmission gate, why one transistors cannot do this, because both PMOS and NMOS has their limitation. So, PMOS cannot transfer a very good low value, similarly NMOS cannot transfer a very good high value. So, that is why, since we want to transfer both high and low value appropriately, that is why we connect two transistors in parallel, and the condition which switches them on is nothing but your clock signal. So, you can think of, I have two such transmission gates to form this mux, 2 to 1 mux. I can have two such transmission gates, and the select lines actually is select lines make sure that I get the appropriate output. Okay. So, if let us say this is okay, this is 1, this is 0. So, I have to make sure that when the clock is high, so this gate should be on. So, for a so I have to put clock bar here, because and clock here, so that the NMOS is on, PMOS is also on, and if this is the 0, then I have to make sure that when clock is low, this is on. So, basically this should be connected to clock and this should be connected to clock bar. So, basically this is your D input. So, basically this is 0, this is 1, and you connect them together, and this is your output. So, this is a 2 to 1 mux. Now, to convert this 2 to 1 mux into a latch, you need to make the connections like here. So, you have to connect the output to input in this feedback, and this is your D, and this is your Q. So, that is how you can implement a latch. So, you see that here also you have only so for a latch we could see that there are basically 4 transistors only, but there is a catch. Here we are assuming that when the clock is low, then this feedback itself will keep my data secure. So, if I had a output which is high, till the point till clock will remain low, I will have a high output here. But as we said, like there is nothing which is no power supply is connected. So, there will be no reinforcement to make sure that the high value remains high. There will be different leakage paths, because of which this value will very soon decay to 0. So, even if my Q was supposed to be high when clock is low, it will not remain high for long duration if I just connect this through this kind of feedback. So, what you have to do? You have to connect again this back to back inverters to make sure that the value remains intact. So, you see, for a latch itself, you are now using, without going into too much detail, we could count 8 transistors, but this will not be sufficient, because you do not want a latch, you want a flip flop. Your resistors are made of flip flop, and a flip flop is basically a combination of 2 latches, one is master, one is slave, and that is why your number of transistors will be much more. Now, the advantage of having a resistor is that you can read the data very in a very crisp manner, because on the clock edge you can read the data, and also your retention, your performance, those things will be much better when you are dealing with the latch. All right. Okay. So, these are the different ways through which we can implement memory. So, we have talked about SRAM, we have talked about DRAM, we have very top level we have talked about how we can implement registers using flip flops. Now, we have not exactly seen what the flip flop is made of, because I think that will digress a bit, but if some of you are interested, we can talk about it more. All right. Now, because there are so many transistors etc., or the construction of latch and flip flops are such that the speed of operation is best in case of all these different options we have discussed about, but the overhead associated with this latches or this register based memories are significantly higher compared to, let us say, DRAM. So, there is this is the trade off you need to be aware of, that at one end you have very high speed memory in the form of registers. On the other hand, you have very dense not so high speed memory like DRAM, but the density is really good. So, you can store lot of data in a small area, and then there is something intermediate which is SRAM. So, which is less denser compared to DRAM, because you need 6 transistors compared to 1 in case of DRAM, but the speed is much better compared to DRAM, and you do not need the refreshing and all these things in case of SRAM. So, this is a more intermediate solution, and it provides like moderate speed which is very good, not as good as resistors, but much better than DRAM, and the density is also better than resistors, but of course not as good as the DRAM. So, these are the trade offs you need to be aware of in terms of different memory technologies which are available and their pros and cons. Now, another thing which you should be aware of before we move ahead discussing about memory is that we generally talk about, let us say, 32-bit memory, 32-bit processor, 64-bit processor or 128-bit processor. So, that means the data I am looking for. So, the data I will be dealing with is 32-bit or so on, right. Now, think about it. Let us say I want to build my memory, and let us say my memory size which I want to build is 32 kilobytes or 32K. Okay. Now, each word I am dealing with is 32-bit. So, if I decide to, let us say, store or design my memory in such a way that, let us say, this is my memory, and each row of the memory stores a 32-bit number, and whenever I need to read this specific row, the addressing will tell me which row I need to read depending on what data I am looking for, and I can basically design my memory such that each row is storing 32-bit. And now, since I have, let us say, 32K memory, so I will have 1000 such rows, right. So, if you visualize this structure, you will see that, and if you can visualize the on the chip how this structure will look like, the structure will look very weird, because it will be a very skinny design, and but very long, because you have 1000 rows and each row is storing 32-bit. So, I am just giving you one such example, but you might have memory which is much bigger than 32K. So, you see that if I want to store only one row, 32-bit in one row, the structure will look very skewed, and then so for reading every row, you will have some address decoder, and you need some connections to all these rows, so that you can read appropriate rows depending on what you need to read. Now the address decoder will be lying somewhere here, and your memory will be this skewed structure. Now the wiring overhead etc. will be enormous, because this structure will be very long. So you will have long wires running from here to here, and long wires are a huge bottleneck in terms of performance. So definitely you don't want to build this kind of a structure. Now what are the alternatives? So you can say that okay, the alternative can be you instead of storing one word in one row, you store multiple words in your row. That looks very logical. So basically instead of 32-bit you store maybe 64-bit or 128-bit in each row, and you try to make this structure as square or rectangle as possible, right? Now when you do that, this is fine for the flowchart and all these things, but your row decoding now becomes little more involved, because it is no longer like one address specifying one word and you get that value. Now the same address, this same row has multiple words. So now which word you need to select, that you have to have that additional information. So this actually will make your row decoding, your column decoding. So you have to now column wise also look at the data. So your row and column decoding becomes little more complex, and as things becomes little more complex, your access speed gets affected. So basically these are the practical challenges in case of memory system or memory technology. So I just wanted to give you this brief overview before we actually jump on to the or using these memories at different levels or as caches, etc. Okay. So I'll pause for a moment. If you have any questions, I'll be happy to answer. Okay, so now just to summarize what we have talked about, I'll in terms of performance, it's important to summarize so that the key things we remember. So memory technology we have talked about, and I'll just put down the trade-offs. Okay. So if we draw a scale where at one end of the scale we are specifying that okay, it has, let's say, low capacity and let's say low latency, so basically very good in terms of performance, and the speed at which you can read them, which is also called as bandwidth. So so basically if you can read multiple bits, multiple so if you have a 32-bit number, if you can read all the 32 bits at once, then the bandwidth will be better compared to if you need to read one bit at a time. So basically if I need high bandwidth, then this is the part of the scale I should be interested in. So how I can achieve high bandwidth? Basically we using more wider ports, basically more number as well as more wider ports. Okay. So and the other end of the scale will have high capacity, so basically very dense memory, and let's say high latency as well, so the speed will be not that good, and then low bandwidth, so bandwidth also will not be very good. Okay. So now we have seen different memories, like we have seen registers or latches, flip flops, etc., register files. Then we have seen SRAM and DRAM. So, in terms of capacity, we have already highlighted that since DRAM can be implemented using virtually with a single transistor and a capacitor. So, the density, the capacity which DRAM provides is very high. So, that is why we can safely put DRAM here, which will provide high capacity, high latency, but the reading writing will take longer, because the you can't have too many ports. The bandwidth it offers is also significantly lower. On the other end of the spectrum, we have basically in terms of performance, if we look at only latency, bandwidth, etc., latches and registers perform best. All right. Now, if you have bunch of registers or you build a register file, so basically you have multiple latches or flip flops and using them you build a register file, then this also will perform reasonably good. But since you will have extra circuitry to decode which latch or which bunch of latch you want to read write, so the read write performance will degrade a bit compared to latches and registers. So, basically after that you will have register file, and finally you have SRAM. Basically in between you have SRAM. So, the SRAM is neither providing you very low latency or very low capacity. It is providing reasonably high capacity, but the latency is also not very bad. Okay. So, this is the takeaway message from our memory technology discussion. Okay. So, if you are asked that basically to comment about this different kind of memories and their performance, so from this you can basically comment on those. All right. Okay. So, now we move to basically why we need cache. So, basically we will motivate ourselves we will try to understand the motivation behind caches. Okay. So, we are already partially familiar about this CPU memory bottleneck. So, we know that like if the processor can do things much faster compared to the memory, and that is why most of the time the processor is waiting for the data to execute before because the data takes much more time to be available. So, if I draw this block diagram of processor and main memory, and if we basically look at their interconnection, their communication between them. So, it has been observed very widely that the performance of a very high speed computer is usually limited by this bandwidth, memory processor bandwidth, and the latency involved there, because the state of the art processors can execute things much faster, almost orders of magnitude faster, several orders of magnitude faster compared to the main memory. So, so the bottleneck becomes this main memory access. And if you look at there are different studies which shows or highlights this performance gap in terms of latency, etc., between how the processor performance have evolved and how the memory performance has evolved. So, if we look at these things, we will see that the main bottleneck comes from this processor memory bandwidth. So, to just to point it out more clearly, we can put it in writing. So, performance of high speed computers is usually memory bandwidth and latency. Okay. So, latency is the time which is required to access for a single access to the memory. So, the main memory latency is usually much higher than the processor cycle time. So, basically let me just write down that main memory latency is much higher than the processor cycle time. So, so this part we will be so why this is the case? Because of the evolution of these different components, or this different like how processor evolved and how memory evolved. In case of memory, there are a very important aspect, that the density of memory has to be high. Now, when you try to figure out the trade off between speed and density, then you see the evolution and you realize that the way the memory have evolved, the read write latency remains much lower compared to the speed at which a processor can process things. So, if the processor can, let us say, run at a clock speed of, let us say, 4 gigahertz, memory will be running at much lower speed. So, in our subsequent discussion, I will show you some basically trend and how the processor and memory has evolved in terms of performance to make this point more clearer. Okay.